Hello everyone. Till last lecture we discussed about the projectile motion, right? We discussed what is a projectile, what is the nature of motion, does the projectile follow under influence of gravity, and what is the locus of that trajectory which we call. So let's discuss a bit brief again on that topic. So if any body is projected with the initial velocity u at an angle theta, so if this is a surface of Earth and it is projected at a initial velocity u and angle theta with respect to Earth's surface, we can easily predict that for how much amount of time this body will be in air, and horizontally how much distance it will cover, even vertically till what height it can go up. So all these parameters we can find out, right? So real life application you can think of like in games like basketball, right? In games like basketball, where a player has to put ball inside a basket which is at some distance. So the type of motion here as well is a projectile motion only. Even you would have come across this game javelin recently. So javelin throw, it also follows this particular kind of motion. So there are a lot of real world examples and you can easily relate to most of them, right? Okay, so let's discuss one more topic in projectile motion today, which is horizontal projection. Horizontal projection. So as the name suggests, right, horizontal projection means the projection is parallel to the surface of Earth, right? It is parallel to the surface of Earth. So let's say if this is some height, if this is some height and some object here is projected with a velocity u which is parallel to the surface of Earth, right? This is the surface of Earth. It will again follow this kind of a nature and it will land somewhere on the ground. So this is a case of horizontal projection. You can think that if some ball is there and you give a push to that ball, the ball will follow this trajectory. Even if a rifle is placed over there, if a rifle is placed and if bullet comes out, it will follow this particular trajectory. So in this particular kind of projectile motion, we need to find what is the horizontal distance this body will come up, and for how much amount of time this body will be in air, like similar to how we discussed for the projectile motion where we projected with the velocity at some angle to the surface, right? Let's derive all that. So based on this figure, let's analyze the motion, the horizontal projection case. So we are projecting a object horizontally with respect to x-axis. So you see the initial velocity is parallel to x-axis, which is u, right? And this body is at a height h from the Earth's surface, capital H. And after projection, when it reaches the surface, it covers a distance r along horizontal surface, which is the range, right? So we need to discuss, or we need to find what is the value of this range, how much time it will take to come up from this particular point to the surface of Earth, and all that. Before doing that, let's understand this is a case of motion in a plane. Everything is in two dimension. Let's identify the parameters in both the dimensions, right? If I talk about velocity, so initial velocity, let's say ux along x direction is what? It is u meter per second. Initial velocity along x is u meter per second. Initial velocity along y is 0 meter per second. Is it clear? Initial velocity y is 0. Why? Because the initial, this is a case of horizontal projection and there is no component of velocity along y axis at the initial point. Again, acceleration along x is 0. There is no force in horizontal direction, right? So acceleration will be 0. Acceleration along y will be plus g, because gravity is the only force and it is acting, supporting the motion, right? So these are my initial parameters, right? Now I need to find, let's start with the time of flight, right? Time of flight is again the time for which this body will be in air, right? So if you see here, so if I assume this as my x coordinate and this as my y coordinate, as always, I know the equations of motion, right? I know the equations of motion. What are the equations of motion? It is Sx equal to uxt plus half axt square and Sy equal to uyt plus half ayt square. These are two equations of motion in two different directions, right? So if I talk about, let's say this is point A and this is point B. So if a body reaches from point A to B, if you see vertically it covers a distance h. Vertically it covers a distance h. Horizontally it covers a distance r. Correct? So again I'm telling, if it moves from A to B, vertically it covers a distance h. Horizontally it covers r. So if I take this particular expression, right? So if sy is h, initial velocity along with y is 0, and ay is z, and t is t square. So if you find out t from here, the t is nothing but under root 2h by g, and this is the same amount of time for which this body will be in air, and this time is nothing but t, which is time of flight. Time of flight for this motion will be under root 2h by g. Correct? Time of flight for this motion will be under root 2h by g. Now let's understand that time of flight is under root 2h by g. Now if I need to find the range of this motion, right? Range of this motion. So do remember that there is no acceleration along x direction. There is no acceleration along x direction. So at every point, if you take, at every point, the velocity along x will be always u. It will be always u, right? Velocity along y will keep on changing, but velocity along x will be always u. So r is the distance covered in x direction, which is horizontal direction. So you can easily calculate distance by the distance, speed and time relation. Since acceleration is 0, so distance is nothing but speed into time. Distance is nothing but speed into time. So if I talk about, distance is equal to speed into time. So distance is nothing but r. Speed, you know, speed along x is always constant, which is u, and time is my time of flight. Time is my time of flight. So this becomes u under root 2h by g, which is my range. So this is expression for range for my horizontal projection, right? Right, so we understood the case of horizontal projection. Now let's solve one problem on projectile motion, right? The problem states that the body is projected with velocity u and angle theta with respect to horizontal. Find its net velocity when it makes angle alpha with respect to horizontal. So let's draw the diagram first. So this is a problem of the projectile motion we discussed. So it is again, the initial velocity is u, the body is projected with velocity u and angle is theta, and let's say this is the trajectory of the body. We need to find that what is the velocity of this particular body when it makes angle alpha with respect to horizontal, right? So we don't know at what point in this trajectory it makes an angle alpha, but we need to find that at that particular point what is the net velocity. So let's say at point P, let's say this is point P, and at point P, let's say this is my velocity and it is making some angle alpha with respect to x-axis, right? At point P, let's say this is my velocity and this is making angle alpha with respect to x-axis, right? Correct? Now if I talk about projectile motion, the very basic concept we know about projectile motion is that the velocity along horizontal axis is always constant. There is no force along horizontal direction. There is no force, hence there is no acceleration, and hence this object will always maintain a constant velocity along horizontal or x direction, right? So if at a point where it is making angle alpha with horizontal, let's say the velocity is v, the velocity is v, right? So what is the horizontal component of velocity here? Horizontal component, this will be v cos alpha, right? At point P, the horizontal component of velocity is v cos alpha, and initially, you know, the horizontal component is x component is horizontal component is u cos theta. So you know that horizontal component of velocity will never change for a projectile motion of this kind. So u cos theta will be equal to v cos alpha. U cos theta is nothing but equal to v cos alpha. What we need to find? We need to find what is v. So v is u cos theta sec alpha, and this is the velocity at that instance where the object makes an angle alpha with respect to horizontal. Now we will discuss one more specific case of projectile motion. We just discussed horizontal projectile motion where we project the body horizontally or parallel to x-axis and there is no component of velocity along y direction. Now the type of motion we will discuss is inclined projection, inclined projection or inclined projectile motion. So in this particular case, we won't be dealing with horizontal level surfaces, but we'll deal with an inclined plane. This is an inclined plane, right? This is an inclined plane which is making angle, let's say alpha with respect to horizontal or earth surface. And from this particular point O, let's say this is O, I am projecting a projectile with an initial velocity u and angle theta, and this is the nature of projectile. This is the nature of projectile. Now in this particular case, a lot of things will change, right? If I talk about, if I take these as x and y axis, we can still say that in x direction there is no acceleration again, because x direction there is no force and hence there is no acceleration. But the problem won't be very simple if I take these coordinates, this type of system as my coordinate system, but rather take, if I tilt this particular coordinate system by an angle alpha, and if I take this as my x and this as my new y, I can easily solve my problem, right? By taking a reference of what we discussed. So what is the difference now? Now the difference, the biggest difference you will see is, now you will see accelerations along both the direction in this case. So in the case of inclined projectile, you will see accelerations along both the directions since my axes have changed. The reference I have changed for my simplification. So now let's find out what is the direction along both the direction. Then we will go on and find what is time of flight, what is range and all that. So yeah, let me indicate what is range first of all. So this is, you can easily say that this is range for this motion. This is range for this motion. This will be the height, max height, right? At any point, if you take at any point, only acceleration is g along the earth surface. Only acceleration is g along the earth surface. This is very clear, right? But if I take components of g, right? If I take components of g, there are two components of g. You see, this is alpha, this is 90, this is 90 minus alpha, and this angle is again alpha. So this will be g cos alpha, and this will be g sin alpha, right? This will be, so this component which is normal to this inclined plane is g cos alpha, and the component along the surface of the plane is g sin alpha. And now I can easily write what is acceleration along x. Acceleration along this new x-axis is nothing but minus of g sin alpha. Acceleration along y-axis is nothing but minus of g cos alpha. Clear? Acceleration along x and y I can easily find out now we will go and find time of flight. Again, time of flight has same definition. For how much amount of time it is in the air, right? Like the time taken from to reach from point O to point, let's say P, is nothing but time of flight. So again, for time of flight, before going to time of flight, we again know that we have two equations here. The basic two equations which we have. One is Sx equal to uxt plus half axt square. Other is Sy equal to uyt plus half ay t square. 1 and 2, right? Let's understand that when this body has covered this journey, it comes back to its mean position, which is the same level, and distance or displacement, not distance, displacement along y direction is 0. So if I talk about at point P, which is the point where time of flight is covered, at that point Sy is 0. At point P, Sy is 0 and time is nothing but time of flight, right? Okay. So if I take this particular relation, right? If I take this particular relation, you know that Sy will be 0, right? Sy will be 0. What is uy? Component of initial velocity along y is nothing but, this is u sine theta, same as we discussed. So initial velocity along x will be u cos theta, Initial velocity along y will be u sine theta. So this is nothing but u sine theta. T becomes my time of flight. Acceleration, I'll write it like g cos alpha and t square, right? Now if you find time of flight here, so time of flight becomes 2u sine theta by g cos alpha. This is my time of flight for inclined projection. Now you see, when the case alpha was 0, which was my horizontal projection and there was no inclination, I could place alpha as 0 and this becomes 2u sine theta by g, which was my older formula. Now what has changed? Instead of g, I have used g cos alpha. Instead of g, I have used what? G cos alpha, which is the acceleration along y direction, because acceleration before was g. Now the acceleration has become g cos alpha here because of the shift in the axis, Find what is the range for this motion. So to find range will appear along my x direction. So this is the max distance which is covered along x. So to find range, we need to use this particular expression, which is first expression here, and I know the time is this, so I can simply put up the values and find what is the range. Let's do that. So Sx, which is r now, will become ux is u cos theta, t becomes my time of flight, ax is minus g sine alpha, and then time of flight square. We just calculated t is given by what? We just calculated time of flight is 2u sine theta by g cos alpha. Let's put up this value here. Let's put up this time of flight here. So this becomes, range becomes u cos theta into 2u sine theta by g cos alpha minus g sine alpha by 2 into 2u sine theta by g cos alpha square, right? This becomes what? This becomes 2u square sine theta cos theta by g cos alpha minus, if I calculate this particular expression, this will become 2 u square sine square theta g sine alpha by g cos square alpha, something like that. I can remove this g and put as 1g here, g cos square alpha, right? This is my whole expression. Now let's see what we can take common and what we can achieve. So if I write it properly, this becomes u square 2 sine theta cos theta becomes what? Sine 2 theta. This becomes g cos alpha, and this is again same, which is 2u square sine square theta sine alpha by g cos square alpha, right? This becomes g cos square alpha. Now if I take let me rub this for you, and if I solve it more, if I take a range here, this becomes, if I take u square by g cos square alpha common, this will become nothing but sine 2 theta cos alpha minus sine alpha into 2 sine square theta. Clear? 2 sine square theta is nothing but 1 minus cos 2 theta. If I put it there, this becomes u square by g cos square alpha, and then sine 2 theta cos alpha minus sine alpha plus sine alpha cos 2 theta, right? Now if I take this 2, this becomes sine a cos b plus cos a sine b, and the final expression which will come is u square by g cos square alpha into sine 2 theta plus alpha minus sine alpha, and this is my expression for range for the case of inclined projection, right? This is the expression for range for a case of inclined projection. So you can easily say that if I put alpha as 0, this becomes what? U square sine 2 theta by g, which is my original formula for the horizontal projection, right? Which is the original formula for horizontal projection. So the calculation is a bit lengthy, but you should know what is the concept here, how we have arrived at this particular expression. You can be given different cases, right? I can give you a case where I can tell you that this is a horizontal plane, and now I am projecting from the top of this instead of bottom. I am projecting from the top of this plane, and this is my some angle, and I am projecting from the top. So this might be the case, but you should know the concept here, how we are reaching to the time of flight, how we are reaching for the this range, and then we will be able to approach any type of problem here. Now let's solve one problem on the inclined projection. So the problem states a ball is thrown from foot of an inclined plane with velocity of 10 meter per second and angle 30 degree with respect to inclined surface. If inclination is 30 degree, find range of the ball on the inclined surface, right? Let's make the diagram. So given is that the inclination of this inclined plane is 30 degree, right? I am projecting a ball with initial velocity of 10 meter per second and angle 30 degree with respect to horizontal, and what am I asked is how much distance it will cover on this inclined plane, which is the range. What is the range of this particular ball? So again we can calculate this by the steps we took, or we have a direct formula as well which we derive. So either way we will reach at the same answer. So if I take this particular expression, right, let's see what all are given to us. U is given to us. U is nothing but 10 meter per second. Don't get confused between theta and alpha. Alpha is the inclination of the inclined plane. So alpha is 30 degree. Theta here is again 30 degree. G you know, G you can take as 10 meter per second square. Now if I put all the values here, I should be able to appreciate and find the range. So range becomes U square is 10 square. G is my again 10. Cos square 30 it will come. This becomes sine 2 theta plus alpha, which becomes 90 degree minus sine 30 degree, and this becomes 10 by cos 30 is root 3 by 2. So root 3 by 2 it becomes 3 into 4, and this becomes 1 minus 1 by 2. So this becomes 40 by 3 into 1 by 2. This becomes 20 by 3 meters. So this much amount of distance it will cover along this inclined plane, which is the range of this motion, right? Which is the range. So we understood different varieties of projectile motion: the normal projection, the horizontal projection, the inclined projection. So again, inclined projection, the case we discussed is when the projection was done from the foot of the incline, right? There might be a case where I'm doing the projection from the top of the incline, right? Let's discuss that in brief. I'll leave that to you, but so let's say this is my inclined plane. Again, I'll draw inclined plane. This is my inclined plane with an angle of inclination as alpha. I am doing projection from here now. I am doing projection from here, and let's say some angle, let's say this angle is theta. I am throwing a ball and the ball is reaching somewhere. The diagram is not very good, but please manage. Right. Let me draw it properly. So this is the nature of this motion. This is falling somewhere on the incline, right? This is the motion. Now in this particular case, I can still use the same expressions. But you can see this theta has become obtuse now, right? Theta has become obtuse in this particular case. Theta is the angle at which projection is being done, right? This is my initial velocity u, and theta is the angle with respect to horizontal. We say here horizontal x-axis is this axis and this is y-axis. So with respect to x-axis, theta is my angle is always measured anti-clockwise, so theta is my angular projection. If I take this angle, let's say this is a theta dash, I can say theta plus theta dash is 180 degree. Theta plus theta dash is 180 degree. Very simple. So range, what I know, range, the formula will be again same, which is cos square alpha sine of 2 theta plus alpha minus sine alpha. Clear? This is range. Now if I want to convert everything to 0 to 90 degree acute angle concepts, what I will do is I'll replace this theta by theta dash. So theta becomes what? 180 minus theta dash from here. So this becomes u square by g cos square alpha sine of 2 theta becomes what? 360 minus 2 theta dash plus alpha minus sine alpha. 360 degrees as equivalent to 0 degree. There is no other way of it. So this becomes g cos square alpha sine of minus of 2 theta dash plus alpha minus sine alpha, right? This becomes like that. You know, sine minus theta is minus sine theta. So again, if I try to take minus common out of this, and if I take the magnitude, you can see that this range will become u square by g cos square alpha sine of 2 theta dash minus alpha plus sine of alpha. And this is the formula for range when the projection is done from the top of the inclined plane or not the foot of the inclined plane. This is the formula for range here, right? So when the projection is done from the top of the incline, this is the expression for range. Let me properly write it somewhere, that if projection from top, but if I talk about projection from foot, the formula for range becomes u square by g cos square alpha. This will become sine of 2 theta minus alpha minus of sine alpha. This becomes formula for range projection from the foot, right? This becomes formula for projection from foot, right? So you can derive all these expressions analytically also if you know the concept, basic concepts of projectile, how we deal with motion in a plane, how can we separately take x and y axis at one at a time and solve different expressions, find time, find range. Yeah, this would be plus of alpha, right? So this was a case of inclined projection, right? So we discussed the normal projectile motion, we discussed the horizontal projection, we discussed the inclined projection as well. Let's go back to the normal projectile motion we discussed and find the equation of trajectory, right? So we already have found out what is the equation of trajectory, and we know that the motion of a projectile is parabolic, right? You will come across what is a parabola in your mathematics, but as of now you understand that if the general expression is y equal to ax plus bx squared, this signifies a parabola which is open towards the y direction, which is open towards the plus or minus y direction. I'm not bothered about which y direction, but towards the y direction. Okay, now equation of trajectory for the normal projectile motion we come across. So let me draw the diagram. If I'm projecting a body at a velocity u with angle theta, it reaches some distance. We know that at any point if I take x comma y will be given by x tan theta minus gx square minus 2u square cos square theta. This is my equation of trajectory or equation of this curve, and by this we can find out any point on this curve. We can find out at one instance. If I know one coordinate, I can easily find other one very easily. But we can also simplify this a bit more. If I take x tan theta common here, this becomes 1 minus gx square by 2u square cos square theta into x tan theta. Tan theta is nothing but sine by cos. This becomes like this. If I cancel out things, y will become x tan theta 1 minus g x by 2u square cos theta sin theta, right? This becomes x tan theta 1 minus gx by u square sin 2 theta. You know, u square range is given by what? You know, the range is given by u square sin 2 theta by g. So if I take g down, this becomes this nothing but the range. This is nothing but the range. So equation of trajectory in simple terms can also be written as y equal to x tan theta into 1 minus x by r, where r is the range. So this is the general expression for the equation of trajectory in terms of range, right? If I know range of the motion, I can directly use this particular relation to find the equation of trajectory. So let's solve one more problem dealing with projectile motion. The problem states that a particle is projected horizontally with a speed u from top of a plane inclined at angle theta. So this is a case of inclined plane, right? How far from projection will the particle strike the plane? How far from the projection will particle strike the plane, right? Now, let's say, let's draw the diagram first. Let's say this is my inclined plane. This is my inclined plane. This is making some angle theta here. This is making some angle theta. And particle is, let's say, placed here at this point, right? So it says that this a particle is projected horizontally. Now the projection of this particle is horizontal. So here it is not at any specific angle, but it is given that this is horizontal, which is parallel to this surface, parallel to this surface. So my u, which is initial velocity, is along this horizontal line, and this is u, and theta is the angle of this inclination. And let's say the particle's motion is something like this, and we need to find where it will strike this plane, right? Like at what distance from this projection point, which is we need to basically find out the range of this particular motion, right? We need to find the range of this particular motion. So here we need to find what is the range, like how much distance is covered along this horizontal plane. So let's go back to our initials and shift that axis, shift this axis by this same angle. This will make our work easier. Before doing that, we know that this angle is again theta, because this is horizontal projection and this is parallel to the surface. So let's say this is my x-axis and this is my y-axis. So this x and y, sorry, x and y, this was my initial. Now I have tilted this by some angle which is theta, and this becomes my new x and new y, right? Let's write the values along all this. So initial velocity along y direction is u cos theta. Initial velocity along x direction, not y direction, y will be what? U sin theta. Again, the acceleration at any point, you see this is g, and you can think of that at this angle will be again theta. The acceleration here is g cos theta, and here is again g sin theta. So acceleration along x is nothing but plus g sin theta, and acceleration along y is minus g cos theta. So you know the initials now. You know the initials. Now we need to find range, right? Let's go by initial approach. Let's find time it will take for this journey, and then we'll find the range, right? So to find the time, again we have the same expression. You know sy is nothing but uyt plus half ayt square. After it covers a time of flight, it comes back to the mean position, and displacement along y becomes 0, because these two point at on the x-axis and displacement along y is 0. So this point, let's say this point is p and this point is o. After it reaches point p, there is no displacement along y direction, so sy is 0. So I can still place 0 here. Uy is what? Uy is u sin theta. T is my time of flight. Ay is minus g cos theta. T square. I can find it T like 2u sin theta by g cos theta. This is my time of flight, right? Now I need to find range. Range is along x-axis. So sx is uxt plus half axt square. I have all the values. I have all the values. Everything is simple now. Ux is u cos theta. Time of flight is my t. 2u sin theta by g cos theta. Ax is g sin theta. And t square you can place again here. 4u square sin square theta by g square cos square theta. Can we quickly calculate what is this value? So this range becomes, this cos theta will cancel out each other. So this becomes 2u square sin square, sorry, not sin, sin theta by g, and this will become 2u square by g, 2u square by g into sin cube theta by cos square theta, right? So range becomes 2u square sin square theta by g plus 2u square by g sin cube theta by cos square theta. Now if I take 2u square by g common here, 2u square sin theta by g, if I take common, this becomes what? This becomes 1 plus tan square theta. because sine square by cos square, and 1 plus tan square theta is sec square theta. So this is my final expression for range. So this much amount of distance this projectile will cover along inclined plane after it comes back to, means till it comes back to the surface, right? From next lecture onwards, we'll discuss more problems on projectile motion in different cases, and we'll be dealing with relative motion concepts, right? Till then, thanks.